Okay, hi everybody. We're going to move forward now in Chapter 9 and move to 9.3. And in 9.3, we're going to take a look at the last two operations of radicals. If you remember, in 9.2, we multiplied and divided. And in 9.3, we're going to add and subtract. So here we go. This is primarily going to be our final rule of radicals. Number 6. It has to do with adding or subtracting radicals. And it's pretty straightforward. To add or subtract radicals, you must have like radicals. Definition of like radicals: the indices must be the same, and the radicands must be the same. Let's just take a look at number 1, and I'll repeat that definition. We have to have like radicals in order to add or subtract radicals. If you look at the radicals here that are being added, they are like. Their radicands are the same, and their indices are the same. If the indices are not the same, you'd have to treat the problem differently and use another skill. You would not be able to add the radicals or subtract them. Now, the principle behind adding or subtracting radicals, which have like radicals, in order to do it, we're making use of a factoring technique. And the factoring technique that we're going to be using to show you how we can add or to subtract is factoring out the GCF. Now, folks, let's take a look at number 1 and notice the addition sign in the middle. Here's one term, and here's the second term. We really have a binomial here. And if we look at both terms that make up this binomial expression, both of these terms share something in common. No, they don't both have a 4. No, they don't both have a 6. But they both have a radical of 11. So in order to show how we add these two radicals together, we're going to have to remove that common factor of the radical of 11, because the radical of 11 appears in both. Now, I also want to mention this, because I know some of you will look and think, well, you know, this 4 and this 6, don't they both have a 2? Yeah, they do. But that is not the emphasis of what we do to show the proof of adding radicals together. It's only the radical part that we are looking at. We're not looking at the numbers on the outside, just the radicals. Now, they both have a radical of 11. So here's what we're going to show. We're going to bring down a parenthesis. And we're going to pull out that radical of 11. And when we pull it out, instead of putting that radical of 11 in the front, where we ordinarily put our GCF, we're going to put it in the back. Now, it doesn't matter whether it's in the front or the back, but it actually belongs in the back in this skill. So we're going to pull out that radical of 11 and stick it right there. Now, how are we going to get the members inside here? Well, we're going to do what we do when we pull out a GCF. We're going to start with this first term, 4 root 11, and we're going to divide it by root 11. And when we take 4 root 11 divided by root 11, the root 11s cancel one another out, and we're left with 4. When we take the positive 6 root 11 and divide it by root 11, you can see imaginary division sign right here. They go, and you're left with positive 6. And now the last thing that we do is we add the 4 and the 6 together, and we get 10 times that root 11, because there's really a times sign there. And there's our given answer. This is the proof that is ordinarily shown to deliver that. Let's go to number 2. We're subtracting. They are like radicals. Indices the same, radicands the same. Both of these terms share a cubed root of 5. Make a house. Pull out that cubed root of 5. And we'll divide twice. This cubed root of 5 will cancel with that 1. And we're left with 1. Because remember, there's really a 1 right there. And if you want to put it there, you can. It goes here for sure. Then the negative 9 cubed root of 5 divided by cubed root of 5. We say goodbye to those two. And we're left with a negative 9. 1 minus 9, negative 8, multiplied by the cubed root of 5, done. Number 3, the radicands are not the same. The indices are, but the radicands are not. And we can't do anything with 7 because it's already prime, and we can't do anything with 3. So we're not able to subtract anything on number 3 because we don't have like radicals. This is your answer. You can't do anything more with it. You can't literally subtract them because the radicals aren't the same. Now 1, 2, and 3 are fine. It's fine when the radicals are like from the get-go. But oftentimes they are not like, and we have to create likeness if we're able to. So let's take a look at number 4, and we'll show you what you will really be tested upon in this section. We're adding. The radicals are not like, but maybe we can get them to be like. Now, we can't do anything more with the radical of 3, but you folks should be able to look at the radicand of 12, and you should be able to identify 2 factors that 12 has, of which one of them is a perfect square. And again, one of them has to be a perfect square. Well, 12, we don't have to do an upside down division for 12. 12 is 4 times 3. 4 is a perfect square. Let's bust this first radical down using the product rule. That would become the radical of 4 multiplied by the radical of 3 plus, just bring this down because nothing more can be done with him. And now let's evaluate the radical of 4, which is now 2 root 3 plus 5 root 3. We now have like radicals. Now we'll make the house. And we'll pull out that GCF of the radical of 3. 2 root 3 divided by root 3, 2. Positive 5 root 3 divided by root 3, positive 5. Let me just stick that answer right here. 7 root 3, done. Number 5. All of the radicands are different. The indices are the same, but the radicands are different. But maybe we can create some likenesses. Bring down the 6. 18 has something, so we're going to get the split ready. 18. should be obvious, but I'll show it. 2, 9, 3, 3. There's your 2 of a kind. 3 times 3 is 9, so in the rational house will be 9, and in the irrational will be that little loner 2. Bring down this plus 3. We'll split that 50. 50. If you see 25 and 2, you're right there. If you need to show the upside down, 2 goes into 50 25 times. 5, 5. There's your 25. That goes in the rational. And 2 goes in the irrational. Then bring down the subtraction sign. And we'll bust up 45. You should look at 45, and you should see probably the most common multiplication fact that would generate 45. 9, 5. 9, perfect square. 5, the irrational house. Now let's swing it back to the beginning. Very slowly. Don't skip steps. Bring down that 6. Times the root of 9, which is 3, times root 2, plus 3 times 5. Root 25 is 5, multiplied by the root 2, minus, pull them out, 3 root 5. Come back. This radical of 2, that radical of 2 are like. He's not. We'll just hold him off until the end. Come back and multiply the 6 and the 3 together, and we'll have 18 root 2 plus, multiply here, 15 root 2 minus 3 root 5. These first 2 terms have like radicals. I'm going to do a shortcut here. I'm down here at the bottom, and I'm going to do a shortcut. The shortcut says, yes, that is our common factor. But the 18 and the 15 are eventually going to get added together anyway. So the shortcut is add the 18 and the 15 together, and we'll have 33 root 2 minus 3 root 5. And that will do it. And we're finished with that. So what you would be tested on in this particular section would be problems like 4 and 5. You are not going to see 1, 2, and 3 on an exam. You'll see something like 4 or 5. Okay, moving right along in 9.3, we're going to continue on and add or subtract radicals. The difference on these is we'll see a little bit more variable action, but everything is pretty much done in the same way. Number 6, negative 7 multiplied by the cubed root of 40 plus the cubed root of 5. So the indices, cube root. Nothing more can be done with him. So we'll have to look at 40 and see if 40 can be busted down so that hopefully one radical that we can get out of this will match him. I pulled 40 off to the side and factored it, and you can see those primes. We have 3 of a kind right here with our 2's. There's going to be our irrational. Down. Times. Make 2. Remember the index. In the rational house, 2 to the third. You could put 8. I'm going to write 2 to the third. In the irrational, 5. Plus the cubed root of 5. Back to the left. Down. Down. Bring down the 2 because its exponent matches the index. 3 divided by 3 will just leave 2 times cubed root of 5 plus cubed root of 5. Negative 7 times 2, negative 14 multiplied by the cubed root of 5 plus, this might not hurt, plus 1 multiplied by the cubed root of 5. Now, if you simply want the shortcut, which I'll take, we take this member of this first term, this negative 14, and add it to that positive 1, and we'll have a negative 13 multiplied by the cubed root of 5. Don't multiply those 5s together. We're not multiplying, we're adding. And that's it. Seven. We're back to square root. We should be able to look at 45 and see a 9 and a 5. Let's bust it. In the rational house, 9. In the irrational house, 5. Along with the a, because there aren't enough factors of a for a perfect square. Bring down positive 7 root 5a because that has nothing. Pull it out. 3 root 5a plus 7 root 5a. They're like. Add the numerical values here because they're like terms. Answer 10. Root 5a to bed. Done. Number 8. Be careful that you're looking at things carefully. It's square root. We have a perfect square right here in c squared. And the 12 has something. So do it slowly. Don't rush. Slow down. Let's bust him up using the product rule. 3. You can't do anything with 3. He's not a square. He goes in the irrational house. Put the c squared in the rational. Minus 5c. 12, we've seen him already. He's got a 4 and a 3. There's the rational. There's the irrational. Come back to the left. Pull it out. The root c squared, c. Multiplied by root 3. Minus 5c times 2 times root 3. Just go back to the beginning. C, root 3. Negative 5c times 2. Negative 10c root 3. We now have like radicals. We can subtract. Take the 1c here. Combine it with the negative 10c. Really subtract. Negative 9c root 3. Done. And then number 9. Index of 3. Looking for perfect cubes. This one is obvious. There's nothing with 2, but n cubed is a cube. 16. I prime factored it over here to the side. You can see it. There's 3 of a kind on the 2's. Let's do it carefully. Down. Times. Split him. Cube root there, cubed root there. That little coefficient of 2, irrational. N cubed, rational. Plus 4n, split him, times cubed root, times cubed root. Rational, 2 to the 3rd. Irrational, 2. Back to the beginning. Down. Down. The cubed root of n cubed. Bring down the n. 3 divided by 3. N to the first is simply n. Times the cubed root of 2. Plus 4n. Times the cubed root of 2 cubed. 2 times 2 times the cubed root of 2. Back. 10 times n. 10n cubed root 2. Positive 8n cubed root 2. They're like, take this variable portion of term here, combine it with its friend here. They're both positive. Don't do crazy with those n's. It's combining like terms. It's 18n multiplied by the cubed root of 2. Finished. Adding and subtracting is a pretty straightforward little item. Now we'll be moving into 9.4, and that'll be straightforward as well when we get to it. I guarantee it when you see it. So we'll come back to you in a few moments.